Welcome to the Problemos channel, Season 1, Episode 3, the episode in which we will dissect two distinct solutions of our first opening mathematics problem, Season 1, Mathematics Problem 1. As a reminder, in the last episode we asked you guys to do two things. First, we asked you to recover the length of the radius of a wholesome sphere, right here. And in the second part of the problem, we ask you to recover the length of the radius of a sphere if that sphere is shattered or broken, and we are either handed the segment or a fragment of that broken sphere, or we pointed at a part of the sphere that is exposed and accessible to us, and the rest of the sphere, let's say, is hidden. If you're watching our episodes out of sequence, then we highly recommend that you first watch the Season 1, Episode 1 and Season 1, Episode 2, because in these two episodes we give the material that explains and motivates everything else that happens on this channel. For example, in Season 1, Episode 1, we give several simple enough yet faithful enough definitions of mathematics, and according to one such definition, mathematics is an art of telling a story of how and why. So now our question is, were you guys able to construct two beautiful stories that are hiding behind these two different parts of the problem? Compare your ideas to ours. At first, we will dissect the solution of the wholesome sphere case. Here, some of you guys probably felt uncomfortable thinking, Roman, you asked us to recover the length of the radius of a wholesome sphere, but you didn't tell us which tools. This is the first lesson that we'll learn in mathematics, and it's the following. In mathematics, there does not exist a codified set of laws which say that this particular problem can be solved using the machinery of only this vaguely defined mathematical layer. There is no such thing in mathematics, which means that when we begin solving a problem, we are in charge, we're in control, and we exercise and enjoy 100% and full freedom of the choice of which mathematical layer will provide us with the machinery that may or will unlock a solution of the problem at hand. It turns out that in this particular case, both of the problems can be solved with nothing more than the Euclidean tools, the Euclidean compass and the Euclidean straight edge. It is always fun to solve these problems in a live audience setting because as students begin coming up with various ideas, the job of a teacher is to channel and to shepherd all that creative energy into a proper solution of the problem at hand. Now, in the absence of the live audience, I'll use a 100% real idea that was suggested by a 100% real student in one of my previous problem solving sessions. That student suggested that because the sphere is wholesome, we roll that sphere into a corner of the room where this line right here represents a wall, this line right here represents the floor, and like I said, this is always possible because the sphere is wholesome. Then that student suggested that to the top of the sphere, let me erase these things right here. To the top of that sphere, we apply the Euclidean straight edge, which will touch the wall at that point right here. At this point right here. And then we know where the wall ends at this point right here. Then the distance from this point to this point can be cut in half with the Euclidean tools alone, and the dead middle of this distance will be precisely the length of the radius of the sphere. Let's name the sphere S, just for the sake of the argument. However, This idea is not acceptable for the following reason in the spirit of professional criticism. First of all, with mathematical precision, it is not guaranteed that the floor and the wall in our room are perfectly square. That's number one. Number two, the top of the sphere is also shaky and questionable. How exactly do we know where the top of the sphere is? What if we're slightly off on that side or slightly off below on the other side? Then we're off and our calculations are not mathematically precise anymore. Lastly, it should be understood that the Euclidean tools, the compass and the straight edge, are theoretical tools, theoretical ideas, and theoretical notions. As we discussed this in Season 1, Episode 1, no single mathematical object exists in real life. The only things that can exist in this context are faithful enough or not faithful enough models or representations of these objects. Consequently, the Euclidean straight edge is a theoretical tool that does not have any thickness or any height to it. In that case, it means that how do we know precisely at which point does the straight edge that looks like a straight line meets the wall over here at the right angle as well? This is another problem. As such, this whole idea or this whole solution is not acceptable, but the idea that is baked into that solution does contain the kernel of truth or the germ of an idea that unlocks a solution of this problem. Can you guys spot this idea at this point? The idea here is the following. What do you guys say the name of this line segment right here? What is this guy? If you said that this line segment is a diameter of a sphere, then technically this is not exactly correct, because this line segment over here is actually a faithful representation of a diameter of the sphere that runs, let's say, from the sphere's north pole to the sphere's south pole. That is not accessible directly to us, but when that diameter is transformed out of the 3 space of the sphere onto the Euclidean 2 space or onto the Euclidean plane that is represented by the wall, then all of a sudden that line segment becomes accessible to our tools, and we can act on that line segment with the straight edge and the compass and seemingly solve the problem at hand. Consequently, if a line segment over here is not acceptable as a solution of the problem, then what is? Here we learn another facet of mathematics. We try to do things as simple as possible, but not simpler. So what other simplest, in some sense, shape can help us solve this particular problem? Well, if a line segment or a degenerate, in some sense, two-gun does not work, then maybe a triangle will work. Why a triangle may work? Notice that right now and right here we are thinking like a mathematician because we're trying different ideas. Sometimes we succeed, sometimes we fail, but we push on. We know that every non-degenerate planar triangle has a unique point, that is the circumcenter of this triangle. That point is equally distant from all the vertices of such a triangle, and the location of the circumcenter of such a triangle can be located precisely with the Euclidean tools alone, with the Euclidean compass and the Euclidean straight edge, by finding the point where perpendicular bisectors of, let's say, this side and this side, let me correct this side and this side intersect. However, what does this triangle have to do with this sphere? Again, at this point, we're kicking ideas around. We're thinking like a mathematician. What will happen if the circumradius of this triangle is exactly the circumradius of the sphere? Aha! This will happen if the circumcircle of this particular triangle is represented by what on the sphere? Correctly, this will happen if this particular circumcircle is represented by a great circle on the sphere. From here comes the first idea. What if we, let me erase this to eliminate the clutter. What if we are able to position 3 points on a given sphere in such a way that each such point sits precisely on the great circle of that sphere? How can this be done? Well, this can be done again with nothing more than the Euclidean tools alone. And the idea behind this particular solution is very straightforward and is nothing beyond the grasp of a motivated middle school student. Look, let's say we're given a point P and a point Q in the Euclidean plane. This was perhaps one of the very first tasks that we all did in middle school when it came to taking the geometry classes. Essentially, Euclid did this task in Book 1, Proposition 1. Officially, he did it in Book 10, Proposition 10. But here we need to construct a perpendicular bisector of this particular line segment. How can this be done? Well, this can be done with 3 lines, 2 circles, one circle centered at the point Q with the radius QP, like so, and another circle centered at the point P with the radius PQ, like so. These 2 circles will intersect at 2 distinct points, this point and this point. And these 2 distinct points will define a unique straight line that will be the the line B, which is the perpendicular bisector of the given line segment PQ. In general, in his very first Book 1, Proposition 1, Euclid caught a lot of grief because he did not prove that these 2 circles intersect at these 2 points, and that is perhaps how mathematicians started thinking about the fact that the number of axioms that Euclid inked in his Elements was not really enough. More axioms is needed, and later on, the German mathematician Hilbert came up with, I think, 23 axioms altogether, but that's besides the point. The thing is, from Season 1, Episode 1, we remember that the geodesic on a sphere is precisely a great circle, which means that we can carry out exactly the same maneuver that we carried out on the plane, but on a sphere. To that end, we take any 2 points on a sphere, let's say point P and a point Q. We can always do that. And then we can open the Euclidean compass to measure the distance between the points P and Q. And remember well that that distance will be the straight line distance between the points P and Q. And we can draw 2 circles. One circle will be centered at the point Q and pass through the point P, like so, on the sphere. And another circle will be centered at the point P and pass through the point Q, like so. These 2 circles will also intersect, just like in the planar case. These 2 circles will intersect at the points A and B right here. And these 2 points will belong Let me take a blue chalk. These 2 points will belong precisely to a great circle, which is the geodesic, which is equivalent to our perpendicular bisector B. So let's mark these points as, for example, A and B. Now, these 2 points will already be the vertices of our triangle that will help us unlock the solution of this problem. However, a triangle requires 3 points. How do we locate the third point that is positioned somewhere on the great circle? Let's name this guy G. And just to make sure that you guys remember what's going on, let us name this circle C1. Let us name this circle C2. And we can say that the circle C1 intersects circle C2 at the points A and B. And both of these points belong to one and the same great circle G. Well, here's another thing that sometimes works in mathematics. If we shake but not stir the situation that we had previously and apply it on the next step, then we can achieve the goal at hand. In other words, if we go back to the plane, if we construct 2 circles that are slightly larger than the existing ones, for example, if we construct a circle centered at Q with a radius slightly larger than PQ, and we construct another similar circle that is centered at the point P, which is the same radius as the previous circle, like so, then these 2 new larger circles will intersect at 2 distinct points here and here. These 2 new points will be also distinct from the previously obtained points. And more importantly, these 2 new points, this one and this one, will still belong to one and the same perpendicular bisector, B, this guy right here. See if you can generate a convincing line of reasoning that this must be so. But the idea here is that exactly the same scenario will play out if we construct 2 more, let me use the blue color here, 2 more slightly larger circles, each of which centered at the point Q and P. For example, centered at the point Q, we'll draw another circle that's slightly larger than this guy, for example, like so. And centered at the point P, we draw a circle with exactly the same radius as the previous one, just like so. And the important thing is that, let's name these guys C4 and C3. The circles C4 and C3 will intersect at 2 new points, this point and this point, which will be distinct from the points A and B. But what's important for us, these 2 new points will sit exactly on the same great circle G. Let's name these points as, for example, D and C. So we can record this over here. For example, C3 intersects C4 at the points C and D, each of which belongs to the same great circle G. So now the distances between the points, for example, A, B, and C, can be sampled directly off of the given sphere S with the good old Euclidean compass. Again, ignore the fact that these points are located on the surface of the sphere. The Euclidean compass, by definition, measures the Euclidean or the straight line distance between these points. But now we have a problem that Euclid officially solved in right here, Book 1, Proposition 22, in his Elements. Don't worry about these propositions. I have the link in the description below for all of these guys. You can look at it later. For now, what is important is that we have the following problem. Given three distinct distances which fold into a triangle, distance AB, BC, and AC, we need to construct a congruent triangle in the plane based on these distances. And this task can be accomplished completely with the Euclidean tools alone. You guys can look at Book 1, Proposition 22, but in more detail, I'll show how this can be done right here. Before I do that, however, I would like to discuss another facet of mathematics called optimization. A computer science algorithm is slightly different from a mathematical algorithm because by definition, a computer science algorithm is a finite description of a finite number of steps that are guaranteed to accomplish certain computational tasks without the human involvement. That is the key in computer science, without the human involvement. The mathematical algorithms, on the other hand, so far, maybe this will change in the future, but so far they need a human. Consequently, in the case of mathematical algorithms, what we talk about is not the perceived time complexity and or space complexity, but the overall cost of an algorithm. In constructive geometry, a cost of an algorithm is assembled from the individual costs of adding a new, not existing in the construction so far line that is added new every time. For example, the act of drawing a circle, this one or this one, adds 1 to the total cost of this algorithm. But naming a point or marking a point does not add anything to the overall cost of this or that mathematical algorithm. So far, our cost of this particular algorithm is 1, 2, 3, 4. So far, the cost is 4 steps. And in order to complete the solution of this problem, we want to optimize it for a minimal cost or a minimal number of steps, which in middle and high school context means basically drawing a new straight line or a new circle. Consequently, in order to construct a triangle that is congruent to ABC, triangle ABC in the plane, we first, for example, mark 2 points, X and Y, draw a straight line through it, then we make these points invisible, and we mark this line as LA, for example. We add 1 to the total cost of our mathematical algorithm. Somewhere on that line, let me use the other color. This is yellow. I'm not sure if you guys can see it, but we mark a point called A prime. That point, A prime, will be a faithful representation of the point A on the sphere. Now, directly off of the sphere S, with the Euclidean compass, we sample the distance AB, and without closing the compass, we carry that distance onto the point A prime, and centered at the point A prime, we construct a circle. Let's say this one. We'll name it circle CA, that has the radius equal to the distance between the points A and B. The circle CA will intersect the straight line LA at 2 distinct points. Which one we pick, it doesn't matter. Let's say we pick this one, and I'll use a different color. Let's say I use the red one. This point will be named B prime. Now, the point B prime is a faithful representation of the point B on the sphere. In general, the two new mathematical objects that we're dealing with right now, the line segment, let me use the blue color, AB, and the line segment A prime, B prime, are different or distinct because the line segment AB is located in one position in space. The line segment A prime, B prime is located in a totally different position in place. These line segments can be also oriented quite differently, and so on. However, in this particular problem, all these details are irrelevant because the only metric or the only characteristic that we care about is the length or the distance between the points A and B and the distance between the points A prime and B prime. And by our construction, that distance is precisely the same. The distance between the points A and B is exactly the same as the distance between the points A prime and B prime. Thus, we managed to partially drag the triangle ABC from the inside of the sphere on to the plane. Here we will not need the entire circle. Let's just, to avoid the clutter, we'll erase that much. That should be enough. Consequently, now we need to do what? Now we need to find the position of the third point or the third vertex of the triangle C somewhere in the plane. We'll name that point C prime. How can we do that? Well, like we said, Euclid does it in Book 1, Proposition 22, but here we give a somewhat simplified version of that construction. And let's see, I'll take this color right here. We open up our Euclidean compass to the distance BC, and without closing that compass, we carry that distance to the point B prime. And centered at the point B prime, we construct a circle of the radius BC. Let's say that circle right here. We'll name that circle CB. And that circle will intersect the straight line LA at 2 points. But we do not need these points. Actually, the point C will be located somewhere on that circle. How do we fix the location of the point C prime? Well, we open up the Euclidean compass to the distance between the points A and C, carry that distance without closing the compass to the point A, and at the point A, let me use this greenish color, we construct another circle. Let's call it circle CC, which is centered at the point A prime and has the radius AC. The circle CC and the circle CB will intersect again at 2 distinct points, but we only need one, so let's say we pick this one. This will be the point C prime, and we now have a faithful representation of the triangle ABC in the plane as a triangle A. Let me use the white color. A, B prime, C prime. That triangle A prime, B prime, C prime is congruent to the triangle ABC that sits inside of the sphere and is not directly accessible to our Euclidean tools. However, now let us count the steps that we carried out. We accounted for the straight line LA. The circles CA, CB, and CC add another 3 to the running total for the cost of this mathematical algorithm. Now we need to construct 2 perpendicular bisectors of any 2 sides of this triangle A prime, B prime, C prime. Which one doesn't matter, but in order to optimize our solution for the number of steps, we want to reuse the circles that we already constructed. For example, let's say we want to bisect the line segment or the side of the triangle A prime, B prime. In this case, we already have this yellow circle CA. So what we do now is we put the needle of our compass into the point B prime, and with the radius A, B, or A prime, B prime, we construct another circle that will intersect the circle CA at 2 points, this point and this point. And these 2 points will define a unique straight line that will be the perpendicular bisector of the side A prime B prime. So it will be this guy. So far we added one more circle and one more straight line, so we add, let me use the other color, 2 more to the total cost of this mathematical algorithm. Now we need to construct only one more perpendicular bisector. Which side we pick doesn't really matter. Let's say we pick this side A prime C prime. We already constructed the circle CC that is centered at the point A prime with the radius A prime C prime. So now we repeat this experiment. We put the needle of our compass into the point C prime. We open up our compass to the distance C prime A prime, and we construct a circle precisely through this, and so on. That circle adds one more. Let's add one more to the total cost of the algorithm. But that circle will intersect the circle CC at 2 points, this one and this one. And these 2 points will define a unique straight line that will play the role of the perpendicular bisector of the triangle side A prime C prime. We construct it this way, and the point where this two, the yellow one and the blue one, perpendicular bisectors intersect, locates the circumcenter of this triangle, and the distance from that circumcenter to any vertex of that triangle is exactly marks the length of the radius of the sphere sought after. That last perpendicular bisector, the greenish one, adds one more to the total cost of this algorithm. So now that we're done with solving the problem of the wholesome sphere case, let us compute the number of steps. 4 and 1, 5, 5 and 3, 8, 8 and 2, 10, 10 and 1, 11, 11 and 1, 12. So now 12 is the number to beat. In some sense, we think that this solution is optimal and cannot be improved. Now here comes hefty and substantial mathematics. Usually such statements must be accompanied with a proof that that number cannot be improved. Just to make sure that you guys understand what have transpired right now, we observe the following chain of ideas. Each sphere has a unique characteristic called the length of the radius of that sphere. Any great circle on the surface of that sphere captures that unique characteristic because the radius of a great circle in the sphere is precisely the radius of this sphere. We can say that any great circle on the sphere captures the DNA of that sphere. Now, we managed to construct a triangle ABC whose vertices sit precisely on a great circle G, which now means that the triangle ABC now carries in it the DNA of a great circle, which carries the DNA of the sphere. Consequently, this particular triangle ABC carries in it the DNA of this particular sphere. But that triangle is not directly accessible to our Euclidean tools. However, we managed to construct or transform that inaccessible triangle into the Euclidean plane, which now is accessible to the Euclidean tools, but because the DNA of the triangle A prime, B prime, C prime is exactly the same as the DNA of the triangle ABC, it follows that the DNA of the triangle A prime, B prime, C prime carries or exactly the same as the DNA of the sphere, and sure enough, by locating the circumcenter of this triangle, we locked in the length of the radius of the given sphere. And that is all that there is to it. And we can move on to the solution of the case of the shattered or broken sphere. Before I move on discussing the solution for the second broken or shattered sphere case, the question meanwhile came up about carrying the compass that was open to a certain distance in the previous solution at any place without closing that compass. Here the situation is somewhat delicate because in his elements in Book 1, Proposition 2, Euclid, with the clever maneuver, showed that it is possible to carry any such distance in the plane from one place to another, and it is not required to close the compass immediately after a particular single operation was performed with it, and he did it by using the material that he develops in Book 1, Proposition 1. However, if we agree that it is possible with a certain set of tools to construct a regular tetrahedron in 3 space, then the ideas that Euclid shared with us in Book 1, Proposition 2 can pretty much verbatim export it from the 2 space into this 3 space, and once we open the compass to measure certain distances in space, then we can carry these distances without closing the compass. Now let us discuss the solution of the second part of this problem, in which we are required to recover the length of the radius of a wholesome sphere that was broken into pieces or not accessible in its entirety. Here some viewers may think, Roman, now you're really asking for something that is impossible. In the previous solution that you just explained to us, we had to draw no less than 4 circles on the given wholesome sphere. That surely requires a good amount of space, and in order to make sure that the distances between the points A, B, and C are practically large enough so we can carry these distances onto the plane, construct the circle, then find its circumcenter, and so on. And that is a valid point. The solution that we presented in the first case really works well for a wholesome sphere, and it is on thin ice when it comes to applying that solution to a fragment or to a portion of a wholesome sphere. Maybe it will work, maybe it will not, so we need to look for a better way. So the question is, does such better way even exist? Do you guys have any idea how can we proceed even if we're given a, let's say, a relatively small fragment of a wholesome sphere? This is where out-of-the-box program declared in the banner of this channel comes in. Some students who took the Euclidean geometry class in middle school may remember Book 3, Proposition 31, also known as the Thales theorem. And that theorem states that the angle in a semicircle, if this is a circle, now let me try to do a better circle here. Is right. In other words, if the vertex of an angle is located on a circumference of a circle, and that angle subtends the diameter of the circle, let's say this is the center, or this is the radius, and this is the radius, then this particular angle is right. So how does the Thales theorem or Book 3, Proposition 31 can help us in this case? Well, again, let us try to think like a mathematician. A sphere is a surface in the old days, or a manifold these days, has one interesting property. The curvature of that manifold, or the curvature of that surface, is one and the same at any point on the sphere. That means that each and every point of a sphere carries a specific information about this particular sphere. The formulaic expression for the curvature doesn't matter, but what is important here is that that curvature is directly related to the radius of the sphere. And what does that mean? Again, we're trying to think like mathematicians. We're trying to creatively manipulate the known units of mathematical knowledge into submission. In this case, that fact about the constancy of the curvature of the sphere means that if we are handed a fragment of a rigid sphere, no matter how large and no matter how small, each and every point of that fragment does carry the information about the unique property of that sphere that we're looking for, the length of the radius of that sphere. So now the question is, how can we extract that information from that fragment? Let us think creatively. Let us think out of the box. What will happen, and this is again a question that a mathematician would ask, what will happen if we take our favorite Thales theorem and rotate this theorem, so to speak, in 3 space about the very diameter of a circle? What will happen in this case? Well, in this case, actually, the semicircle would have been enough, but the whole circle works too. In this case, what will happen is that the circle or a semicircle will actually generate the sphere at hand. And as we rotate, for example, this semicircle about its diameter in 3 space, this point, let's call this point P, for example, let's call this point S, let's call this point P prime, actually S prime and T prime. That point P prime, as it rotates in space about the diameter of this semicircle, will trace a circle on the surface of that sphere. If we project the point P prime onto the diameter into a point, sorry, this guy will be North Pole prime, this will be South Pole prime, into a point that we'll call T prime, for example. Then the distance from T prime to P prime will be the radius, let's erase this guy, do not get confused by it, will be small r. So the distance from the point T prime to P prime will be the radius of that particular circle. So now, can we connect this helper circle with a fragment of a wholesome sphere that we were given? Sure we can. As a solution now, the following steps emerge. If we name, let's say, logically, the bottom of this particular fragment as S for south pole of the whole sphere, which is not available to us, we put the needle of the compass into point S, and on that fragment we draw a circle. Let me draw it in blue, like so. Then, what can be said about this circle and about this point S? Well, if we take any point, let us call this point P, on that helper circle, let's call this guy C, then that fragment will carry in it a notion of a diameter, which will be located here if we complete the sphere. And if we project the point P orthogonally on that diameter, then we'll obtain the point T, and the distance between the point T and the point P will be exactly the radius of that helper circle C. However, the distance between the points S and P can be what? The distance between the points P and C can be sampled directly off of the sphere. Let's call this distance D, with the Euclidean compass. In order to sample that distance, all we have to do is open up the compass and measure the distance between the points S and P. Again, that distance is a straight line or the Euclidean distance. How does that help? Well, now we should be able to see that the distance between the south pole of the virtually wholesome sphere S and the point P taken anywhere on the helper circle C will be faithfully reproduced by what? By the distance between the points S prime and P prime. And what is missing in this picture with this fragment? What's missing is another line segment that runs directly into the north pole of the sphere and is represented faithfully by the line segment P prime N prime, this guy right here. And now the only question remains, since we can sample the distance S, P, or D directly off of the fragment of the wholesome sphere with the Euclidean compass, how do we know the radius of this helper circle R, or how can we recover the distance from the point T to the point P? Well, essentially, we already answered that question when we presented our first solution, with the exception that in our first solution, we dealt with a great circle of a sphere by taking, let's say, points A, B, and C on that great circle. But in this case, we don't have a great circle, we have a smaller auxiliary helper circle, but here we can choose any 3 points on that circle that we want. For example, we can take, let me use the yellow color, we can take a point here, here, and here. Call these points A, B, and C. Measure the distances between these points with the Euclidean compass. Obtain this triangle that still sits nicely inside the fragment, but with respect to the distances A, B, B, C, and AC, we can repeat the very same algorithm that we described in our first solution. We can construct a faithful representation of the triangle ABC in the plane and call it A prime, B prime, C prime, like we did in the first solution. Find the circumcenter and locate the length of the circumradius of that helper triangle, and that length will be exactly equal to the length of the radius of that circle. So now the solution of this particular problem should be evident. Let me erase this helper drawings temporarily so that you can guys rewind and watch this if you need to one more time. But the overall solution now is the following. We draw a straight line L that will represent a diameter of a future wholesome sphere. That will add, as we know, 1 to the cost of this new algorithm. Next, anywhere on that point, anywhere on that straight line L, we pick a point that we will, let me do it with the same color. We'll call this point T prime, and that point T prime will be a faithful representation of the point T located on the diameter of the sphere of which we're given a fragment. Next, through that point T prime, we construct a straight line. We'll call this guy LT, that is perpendicular to L, and that particular task can be carried out in 3 steps. So now we add the total cost of 3, and here we'll record that the line LT is perpendicular to the line L through the point T prime. Next, because we already computed the length of the radius of the helper circle, which costed us 12 steps, 12 steps. We'll write them right here. Now we open up the compass to the length of the radius that we recovered through this 12-step algorithm, and we construct, let me do it with yellow, a circle centered at the point T prime with the radius equal to the length of the radius R. Let's like it this way, for example. Let's call this circle CT. Now the circle CT will intersect the straight line LT at two distinct points, and which point we pick doesn't matter. Let's say we pick this one. And this point will be a faithful representation of the point P that is located on the fragment that we are given. We can even write it down and say that the circle CT intersects the straight line LT at 2 points, of which we're interested only in one, and the other we don't care about. So we can actually, even to eliminate the clutter, erase a little bit here. Now that we have the point P prime located, we go back to our fragment, open up the Euclidean compass to what? To the distance SP, which we can do and sample that distance directly off of the given fragment without closing that compass, because remember my earlier comment, now we can do that. We carry that compass to the point P prime, and with that radius SP, or the distance D, we construct, let me use the red one, a circle centered at the point P with the radius SP or D, like so. And we will name this circle, for example, CP. Again, the circle CP will intersect the straight line L at two distinct points. Which one we pick, in theory, doesn't matter. Let's say we pick this one right here. So that point is a point S prime, and that point is a faithful representation of the south pole of the fragment of the wholesome sphere S. And consequently, we know, let me use red, that in theory this will be a straight line that passes through the points S prime, P prime. We were only interested in this guy. So the line segment S prime, P prime is what? That line segment is a faithful representation of the line segment SP. This guy shown in red. What do we need to do now? Now we need to construct a straight line that is perpendicular to this line segment S prime, P prime, and passes through the point P. Let me use the, which color did I use? Blue one? Let me use blue one, for example, this way. And let's say this guy must be perpendicular to this line. This line will intersect the straight line L at the point N prime, which is a faithful representation of the virtual north pole of the wholesome sphere, of which we're given a fragment. And now, according to the Thales theorem, since this angle is right, this line segment N prime, S prime, will be what? That line segment will be a faithful representation of a diameter of a virtual wholesome sphere. And what else do we need to do at this point? At this point, we use the Euclidean tools to cut that line segment in half, and by doing so with the perpendicular bisector, call it B, locate the point O where these two straight lines intersect, and the distance from, let's say, we'll call this guy O prime, from O prime to N prime, or from O prime to S prime, that distance right here is exactly the distance R. So what is the total cost of this algorithm? When we accounted for 12 steps over here, we already constructed the straight line LT, and we constructed a circle CP. That adds one more cost for constructing this red circle CP. Then we constructed a straight line S prime P prime. That's another step right here. And we constructed a straight line, this one, through P prime perpendicular to this. That's another 3 points in complexity. And once we obtained the point N prime, another 3 steps to construct the perpendicular bisector B that actually locates the point O prime and reveals the length of the radius of the given fragment of a wholesome sphere. So now let us do a little bit of arithmetic. 1 plus 3 is 4, plus 12, 16, 1, 17, 18, plus 3, 21, and 3, 24. So the total cost of this algorithm is 24 steps. Now we can discuss the quality or the perceived quality of our mathematical algorithms. On paper, by the perceived complexity, our first algorithm costs 12 steps, and our second algorithm costs 24 steps. It seems that our second algorithm, that is suitable for a fragment, but will also work for, obviously, a wholesome sphere, because we have plenty of room, and on a wholesome sphere we can always construct a one circle, seems to be twice as expensive as the first algorithm. However, in my personal, humble, and not professional opinion, the words that can describe the first algorithm are intellectual finesse. Because look, in the first case we had to know a little bit about how spherical geometry works. For example, we had to know that if two circles are drawn as we explained before, they will intersect at 2 points that belong to a great circle of a sphere, and 2 more circles will generate 2 more points, each of which will sit precisely on the same great circle G. That is a little bit of a knowledge that we need to possess when we step into this problem. Thus, intellectual finesse for the first algorithm. The second algorithm that we described over here can be described as elegant or very elegant, because we did not really need to know much about how spherical geometry works. All we had to possess is basic situational awareness or basic street smarts. Just about the only thing that we had to do specially is out-of-the-box thinking of rotating the said Thales theorem or book 3 proposition 31 around the diameter of the circle at hand. The rest of the solution unfolded pretty naturally and did not require anything that goes beyond the middle school geometrical course curricula. Also, now let's step back a little and reflect on our experience. In order to generate both of these solutions or both of these algorithms, we did not crunch numbers, we did not shuffle symbols, we did not manipulate formulas. We creatively manipulated the known units of mathematical knowledge into submission. And by so doing, we put our mind into a mode that was faithfully close to the mode in which the mind of a professional mathematician operates. And that is why we do these particular things on this channel, and that is why we do these particular things in this particular way. In Season 1, Episode 2, in the previous episode, we described how to solve mathematical problems correctly. As the fourth step in this process, we're suggested to generalize and to abstract the solutions that we obtain. In this particular case, one way to generalize this particular problem is to inquire what set of tools will allow us to recover with mathematical precision the lengths of the semi-axis, for example, of an ellipsoid. Ellipsoids usually come in two flavors, the ellipsoids of revolution and the ellipsoids of not revolution, and depending on which one we choose, the solution may be different, but that is perhaps one way to generalize this problem. However, in order to abstract the solutions of these two parts of the problem, we need to think at an entirely new or higher level of abstract cognition. If you guys can answer that question, and if you can abstract the solutions of these two cases on your own and do it correctly, in other words, compress everything that we talked about into just one or two sentences, then you will be able to solve the next problem that I'm about to give you correctly and on your own. Are you guys ready for your next challenge? Are you guys ready for S1M2 or Season 1 Mathematics Problem 2, in which you will not have to crunch numbers, you will not have to shuffle symbols around, and you will not have to manipulate formulas? Again, in order to solve that problem on your own, should you decide to do so, you will have to think like a mathematician. Why? Because in this problem, you will have the following challenge. Given a cube, let's say this one, this guy, right here, given a cube with the length of its side doesn't matter, let's say A, we have a curious ant who is sitting at the vertex of that cube named A, and at the end of the day, the ant is tired and it wants to get to the diametrically opposite vertex of that cube. Diametrically means all the way across over here. Let's say we'll name this vertex B. In a shortest possible way, in other words, the objective for this ant is to crawl over the surface of that cube somehow, not through the cube, not out of the cube, flying or whatever, but strictly by crawling on the surface of the cube somehow and traverse a path that is the shortest possible of all the paths from the vertex A to the diametrically opposite vertex B. Again, we highly recommend that before you take on this problem S1 and 2, you decide to abstract and are able to abstract the solution or both solutions that we presented for the problem S1 and 1. As a fair warning, it will be difficult. It will not be easy. That abstraction will require you to think at a higher plane of abstract cognition. However, if you will be able to do so, then chances are high that you will be able to solve this particular problem, S1 and 2, correctly and on your own. We wish you the best of luck. This is it for this episode. Thank you very much for watching. Thank you for your time. I'll see you guys in the next episode.